Hello, my name is Jolly Swires. I'm a senior engineer. I've come down with COVID, so you must excuse the voice, but let's hope it sounds a lot better on this professional microphone. Um, the code I want to take you through today is something called TunePid 2. The 2 is because I did something similar before. So, what PID stands for is Proportional Integral Differential Controller. And I'll show you the algorithm for that. In fact, right now, um, so you see, it has something called accumulation of error, which is plus equals delta time. That's effectively the integral. The accumulation of error is truncated to pi over 8, which is 45 degrees. I did that so that it didn't go massively over and could effectively spin around on the spot, because it can do that, and that is no good. The derivative error is error minus last error, so just the difference divided by delta time, and the last error equals error, and the output equals Kp proportional, Ki integral, Kd differential. The effects of these are, so this is effectively saying the output will be proportional to the input error. So that, if you think about it, that's quite a reasonable statement. And then this one says accumulation error times Ki. So that's saying if the error is staying the same, then there will be an accumulation of error which will increase, and so it will go up to match that the output will match the error, even if there is a static difference. And the differential, what that does is effectively dampen down. So it's saying if there's an acceleration, then dampen down the output. Anyway, let's hope that makes sense. So anyway, this code consists of some globals. You see these 2D points. The 2D point there, and it's quite simple class, just an X and Y double. Some of these values don't look like they should be a 2D point, but aren't. Apologies for that, that's probably just some slack coding. You can see the go button and the J-frame called PID tune. And also note the acceleration. The acceleration is G, the lowercase g for Earth. When working with Unity, that tends to say 0.981 is G, and then so this will be effectively 10G. Whatever. I don't know why Unity does that. It's almost like it puts gravity into slow motion by tenfold. But anyway, this matches the code exactly for the Unity. So the PID thread consists of really two systems. There's a runner, and threads obviously have a run method. And so if I show you, yes, I will show you the two. The two runners. So genetic. See that The green on the right hand side, that is you, and that's the pirate missile that got launched. And the you see, it didn't do too bad, but I would have thought there's room for improvement. And if I show again, this time the genetic. This is essentially a single thread doing multiple things. You see on the bottom, that's the proportional, integral, and differential constants, and that's the distance, the minimum distance that it reached. See, the first one is actually quite good, and then it went up a bit when it tried the next combinations. It came back down to 21 in that one, so that's quite good as well. Note that it's got two constants which are positive and a differential which is negative, so that will be subtracting the negative score from the output, and that one's even better. Look, 2.20. Anyway, what you can do is you can stop these at any point, and then just type them in. See there? Put an F at the end to make sure it's floating point, not double, because that's what Unity uses. So let's have a look at the code in more detail. So that's essentially the runner is this. See, it waits for the button to be pushed. So if not start, and the button when it's pressed sets start to true, then it does an init, and that's just setting up the initial parameters of the two bodies. So the pirate has got a speed, you've got a speed, you've got a location. So that's what the init does. This is what I was talking about with the things that maybe should be 2D points. So these are doubled out, but it's probably just a bit of slack coding, don't worry about it. This while start, so once the button is pushed and start equals true, it goes into this loop. This loop goes to there. Yep. This if quits a loop effectively if the enemy is getting further away and not coming up to the target, so it will quit the loop, and then it will set start to equal to false, which quits the loop, print out bang, and break. So it'll break from the loop and go down to that place that showed you. This is the special startup case. So it's in the initial, when the initial index is 0, set the initial direction to be the difference in positions, and that's the amplitude. I don't think we use the amplitude, I'm not sure. We might do for normalization, and it works out the initial theta has been the initial direction y divided by the initial direction x, and doing arctan 2. The idea is that I wanted to start at a 0 condition, so this error here will effectively be the same as the initial theta error. So when it subtracts it to, it will be a 0, and then the output starts at 0. Then PID does its thing, and then output equals PID working on output. This is essentially a rotation to, I don't know if you recognize this, but it's standard two-dimensional rotation around the Z vector. And it does output plus initial theta, so it's adding back on that initial theta. So it means that the output shouldn't really go much beyond 45 degrees or whatever, you know. And it should be incremental, so that these velocities, as you can see them worked out, it adds a 2-point position Y, so it's doing velocity, and this is acceleration, and it's doing position plus equals velocity, and then so that's the enemy velocity, and position is recorded in the linked list. Well, I think it's just a list, and your position is calculated as well by just multiplying delta time by your UV and plus equals. So incremental, and then it's doing a PT repaint, and that's just so it outputs everything on the scene. It's saying if the index is greater than 10,000, then quit. So there's a fixed limit of how far it will go. Sleep 10, just to give it some animation base, which equals delta time. I think the delta time was 10 over 100, so it's the same. Yep. And then here you can see it after the loop, declaring E and setting up the initial parameters for the explosion. And it's doing a repaint of that and sleep 10. And then it's setting E to null. Now what corresponds to that is the paint. So this is called every time repaint is used. So it's getting the width, getting the height. Fill rectangle, make a nice black rectangle. If enemy is not equal to null and you're not equal to null, then it tries to draw the enemy positions. And then if E is not equal to null, then it draws G. Simple as that, really. It's really this is being instructed to draw the scene, and that's what it does. So if we go to the paint demo, just something I cribbed from a paint demo from a book, so it kept the name. It's a bit unfortunate. I should call it something else, really. But it sets up your J-frame. This is the go button, and you see it does start to not start, so it toggles. So in theory, you can get out of that loop by hitting the go button again, and it will stop the animation, and then move on to the explosion. Temp add go. Temp is a J panel, so it's adding the button, and it's putting it up top in the north, and putting the PT, which is the thread, which is also a J panel, in the center, and it's setting it to visible. Just let's have a quick look at the main while we're here. You see this is switching between genetic, which is pt.thread genetic algorithm, and runner, which is a paint demo and start. As you can tell, he starts a thread with start, and off she runs. So that's really all I want to say about the runner. If we look now at and that was the unit 2. I didn't cover that. That's essentially the set points and set velocities that I've set. Unit 2 is used for the chromosome and the genetic algorithm. We'll close that up. So init 2 has a set of random things. See, rand comes in, and that is just a random 0. So it's seeded to 0, and these are just random velocities and random positions, and it's setting it, as you can see, to the my position MP and enemy position, which is always 0. Enemy velocity, which is always 0, but your velocity is up to 200. Oh, I see. Yes. So it's minus 0.5. So that means it will go roughly minus 100 to plus 100. But it will be rand. So the idea we're using rand is that the scenes will always be the same, and that will go for the full 100. If we have a look at the chromosome, just simple k proportional, k integral, k differential, and distance squared. So the distance squared starts off as null, and then when the thing runs, you get a distance squared for each one of the tries. So that's just a null pointer thing. I didn't do getters and setters for this. It's just not worth it. And the toString is nice because it prints out, as you can see, these values, and you can see the distance squared, so you can make your own adjustment. So the genetic algorithm is here, and it starts with setting 2,000 guesses, running on 100 scenarios, and I've shown you the rand, sorting to nearest, farthest, last. So it sorts them all into a list, nearest first, and as it says, farthest last. And then it breeds, so the best two get bred together for 2,000 iterations, for 2,000 guesses. And then there's a mutation of, I think it's actually 5%. I'll just double check. Running same 100 scenario, go to 3. So it goes back to that and keeps going. So it's an infinite loop. So let's show you that. See, that's the generation of the chromosome with random values. So it's essentially setting minus 100 to plus 100. And the reason why it's copy of run is because it was essentially taking the run value, the run method, and copying it. But it's a bit simpler than that now. So it just it just does a full end-to-end run with no waits. So there's no thread sleeps in there at all. So it just uses the maximum CPU values. I've not made it multi-threaded because it would be a faff. Because of all the globals, and you can see what it does. It does number of sessions is 100. Distance squared equals copy of run. So copy of run is one sequence, which you saw with the red line and the green line. And as I said before, when it hits the situation where it's moving away from the target, then it quits, and then that becomes a distance squared, which is measured and returned. So this is the location 3 while true, and this is the sort. You can see the comparator, just effectively taking distance squared and working things out. Yep, and that's printing out the, well, it's just printing out one. It's a bit complicated, but it doesn't need to be. it did print out 5, the last 5, but I don't do that anymore. I just print out 1. And here you can see it breeding. So you say, well, you know, if the random value is above 0.5, then top 2 equals newborn, and if it's less than 0.5, then top 1 equals newborn. And newborn is modified by plus or minus 5%, as I thought, and added to newborn, and it does that 1,000 times. So it's a guesses as list. Size, so it's 2,000. And then here we go. So it runs a copy of run again, and generates a new list, which is then kicked back up here, to do the sort, and that's it. And you can see the use of the seed random 0 to make sure all the scenes are the same. Copy of run. I'll give you a quick look. As you can see, it's pretty similar to the code for the run. It returns no, or the closest point of approach, which is that. And that's it. Thank you very much. Okay.